Hello everyone, I'm Xintong Li from Tsinghua University. Today I'm here to present our work HYTE, flexible tiling for sparse accelerators via hybrid static dynamic approach. Let's begin with sparse tensors. Sparse tensor computation with varying degrees of sparsity is widely used in graph computing, fluid dynamics, 3D point clouds, and sparse neural networks. The various sparsity requires a more flexible hardware. This talk focuses on the sparse tensor multiplication, SPM, SPM. We denote AIK and BKJ as the input tensors and CIJ as the output tensor. Different data flows can be implied. A widely used example is the Gustavsson data flow or row-based. It scans non-zero elements AIK in the tensor K, then uses the column index K to fetch a corresponding row of tensor B, multiplies them, and accumulates the result into the row I of tensor C. Another key concept in our title is tiling. We all know tiling lets parts of the data to feed in the limited on-chip buffer, improving the reuse and alleviate memory bottlenecks. A tiling strategy is defined by the number of non-zeros per tile size, the shape of the tile in each dimension, tile shape. Note that the coordinate tiling is used in sparse accelerators to avoid coordinate mismatch. Finally, the iteration order across each tile's intertile order. Specifically, if we iterate over the I dimension, the B with coordinate K and J will not affect it. So it can stay in the buffer and be reused. So what makes tiling sparse tensors different from the dense ones? First, sparsity varies across tensors and even within the same tensor. For sparse regions, it will underutilize the buffers, while for dense ones, it can cause memory access misses. Second, compressed formats like CSR will add overhead from extra metadata accesses. To mitigate the buffer underutilization from irregular sparsity, Taylor's allows a fixed percentage of the tile size to exceed the buffer limit. It statically sets the overbooked tile size and fixes the tile shape by expanding on the K dimension first, then J. From another angle, DRT supports non-uniform tile shapes. It is chosen greatly at runtime based on the data. The growth order is fixed, which is expanding in K first, then I, then J. To enable this, data is preprocessed into macro tiles. HARP also uses the dynamic grading strategy, but to cut the pre-processing and hardware cost, it tells only along the I dimension, which is the easiest way to tell, and skips the J and K. In summary, existing works use either static or dynamic method and apply fixed strategy to the different tensors. Each method performs well on certain tensors, but poorly on others. To achieve optimal tiling across diverse tensors, we first summarize the design space of sparse tiling, including the tile size and shape, the dynamic static decision, and intertile order, and the buffer management. Next, we are going to analyze these parameters' influence of each factor and propose the corresponding solutions. Considering the tile parameter first, large tile may load to the data and not fit in the buffer, introduce more memory traffic. But on the other hand, smaller tile on one dimension will cause repeated access to the tensor not aligned with that dimension, introduce more memory traffic of other tensors. For example, tiling along J leads to repeated access to tensor A. Note that the repetitive tensors varies according to the tile dimension you choose. As a conclusion, we want to balance these two overheads. For the tile size parameter, on denser tensors like the purple one, the reuse benefit dominates. So the smallest tile size is 0.5 the smallest tail size which can avoid the overflow is ideal. In contrast, for very sparse tensors like the yellow one, data reuse is minimal and repeated access dominates. So a large tensor set is preferable. As a conclusion, a fixed overflow strategy cannot adapt for all tensors. Additionally, different tensor computation involve different sparsity levels in tensor A, B, and the output C. For sparse output tensors, tidying along the K dimension, which are related to C, only incurs little extra C accesses and is the ideal selection. However, for denser output tensors, tidying K incurs a high cost in accessing C repetitively. So other dimensions are more suitable. As a conclusion, different tensors call for tidying in different dimensions. Furthermore, a purely static optimal strategy may not suit all tensors, while a purely dynamic greedy strategy lacks global perspective. Therefore, we aim to combine both. In addition, the intertail loop order determines which tensor benefits from the reuse, as we introduced earlier. When the non-zero size of C is large, then traversing the K dimension first allows to better reuse of C in the buffer. Conversely, when the non-zero size of C is very small, then traversing J first is better. Thus, the optimal intertail loop order varies based on the relative sizes of A, B, and C. Finally, since different computation require reusing different tensors as the previous slide, the buffer must support various allocation strategies. In addition, different tensors have diverse ratios between data and metadata, and also require flexible buffer allocation between these. Hence, different computation require different cache allocations among A, B, and C, as well as between data and metadata. To summarize our motivations, first, we want to meet all these 5 demands previously discussed. Second, fully flexible dynamic approach is too complex and does not offer global awareness, so we adapt a hybrid static dynamic method. From the software perspective, we select appropriate strategies based on each sensor's features with dynamically local fine-tuning during the runtime. And from the hardware perspective, we ensure the configurable support for all the relevant parameters we discussed. This leads to our overall design and interface. In the static offline phase, the static software scheduler takes the input tensors and hardware specs and outputs an initial configuration for all the discussed parameters. In the dynamic phase, first, the initial configuration generated by the static scheduler are loaded. Then, during the runtime, the scheme is further fine-tuned in response to the behavior of recent tails. Let's now look into our scheduling strategy first. Our goal is to understand the characteristics of each specific tensor so that we can select the most efficient scheme for it. Since the original tensors are large and processing the whole tensor would be costly, we use a lightweight sampling and estimation approach. By analyzing just a small portion of the tensor, we can efficiently extract the key parameters we need. So what are the required parameters that will affect the performance? Unlike dense computations, optimized sparse computation depends not just on the tensor shape. Since zero elements are skipped, so the memory performance is determined by the number of non-zeros, NZs, in tensors A, B, and C. And total computation is based on the effective max. Well, NZ A and B are already known. NZC and effective max are unknown until the computation. Tidying introduces another parameter. Tidying along the K dimension causes the repeated rise to partial C tensors. We define NDCTK as the sum of all those non-zero C partials across all the non-zero C partial data when the K is held with the size Tk. This differs from NDC, which is the union of all those partials. There is an extreme example to illustrate this concept. In the fully dense scenario, all partial C tensors are dense, so NDCT K equals NDC times K over Tk. And for the fully diagonal scenario, partial C's don't overlap, so the NDCT K just equals NDC. To estimate the effect MAC and NDCTK with minimal overhead, we sample part of the input tensor and estimate the parameters based on the sample. Effect MAC is estimated by the sampled MAC over p squares, where p is the sample ratio. For NDC and NDCTK, we use a hash-based estimation method on the sampled region. The hash function simulates the merge of partial C's with the same coordinate, allowing the NDC to be estimated using the K's smallest hash pair. NDCTK is estimated similarly. Once we have the estimated parameters, we search the prune design space for the candidate strategies. A constant time cost model estimates each candidate's performance using its mapping scheme, estimated parameters, and hardware configurations to select the optimal strategy. For concrete examples, on the left, the power law tensors NDC is 18 times larger than the input, with NDCTK increasing 8 times. However, on the right, for almost diagonal tensor, C is only 4 times larger, and NDCTK increased by 30%. Thus, the right tensor is better suited for tiling along the K dimension. For hardware design, to support the flexible design space, we introduced a tiling controller to manage the configurable inter-tile orders and preserve the metadata from compression. For the intra-tile access, we add accessors to handle access to the truncated compressed formats, including the coordinate checks and metadata management. To flexibly allocate buffer space between metadata and data, we use a dual-end growth buffer manager, which means the begin address of the data and metadata is from the top and bottom respectively and increased to the middle. This approach ensures high buffer utilization regardless of the ratio between data and metadata. For example, in a relatively sparse sensor, there are fewer non-zero elements, so the metadata takes up more space. In contrast, in a denser tile, as the lower shows, the actual data dominates, requiring a more space than the metadata. To support dynamic fine-tuning, we record the access count of the 4 subtiles within each tile during the execution. In the example, let's assume we have a B buffer with 2 slots. The original tile has 4 non-zero elements, so the hit rate is 0.5, since only 2 out of 4 can fit in the buffer. By using the recorded subtile counters, we can estimate the hit rate if we further tile along the K dimension. It becomes 0.75. And if we further tile along the J dimension instead, the hit rate improves to 1. These hit rates, combined with the estimated parameters, help us to decide whether it's better to use a smaller or larger tile, and determine the best shape to adjust for the optimal performance at runtime. For evaluation, we use the previously discussed 3 methods as baselines and test under the typical hardware configurations. In the overall result, the Taylor's DRT and HARP each performs well on different tensors, while HYTE achieves at least 3.3 times speed up on average. Breaking down our optimization contributions, the intertail order and allocation, tiling size, tiling shape, and dynamic tuning achieves the average speed-ups of these times, respectively. To summarize, we first presented the design space of sparse tiling and analyzed new tiling characteristics introduced by the sparsity. To address this, we implement the co-optimization in both software and hardware. In software, we employed sampling and estimation to derive global static strategy. And in hardware, we enabled support for flexible configuration and local dynamic adjustments based on the tensor-specific characteristics. And this is all my talks. Thank you for your listening.